Now let us look at a general scenario. Let us say we have a beam which is extending. So, I am just going to cut off a small portion here and look at what forces exist within that. Okay. Since I am sectioning at these 2 points, we will have shear forces acting like this. I am just drawing the positive sense always. There is a moment acting here, shear. What is the positive sense here? It is like this, okay, and this could be x1 and this could be x2. Okay, so M at x1, V at x1, M at x2, V at x2, and there could be some load acting in between. So, let me call that as W of x per unit length. Okay. There could also be moments. For now, let us assume that we have no concentrated or distributed moments directly acting on this beam. We need to find a relationship between all these quantities that we have, M and V and W. Okay. How do we go about connecting these? We can use equations of equilibrium here in order to make a connection. Okay. Let us do that exercise a little bit more rigorously. So, I am going to take, let us say this is the reference point, there are some forces acting. Let us say I am bothered about a section at x, okay, and I would like to know how the shear force V of x and M of x is varying. Okay. Now, one way to do that is I can section a very small segment at x, let us say dx, and examine that particular small element. Okay. Let us do that exercise and see what we have. So, this is a length which is just dx in length. This is x away from one of those reference points. There will be a load acting on this, okay, with no loss of generality between this, within the small length dx, the variation can be neglected and we have W over here, W at x, okay, per unit length. Okay. This is the external force that is acting transverse in direction. Okay. Now, let us draw the bending moment. This has a negative sense like this, and therefore, we will have this is the positive sense of shear force V at x, and bending moment will be like this, which is M at x. Since we have cut this side also, we have moment and shear force. This is M at x plus dx, because I am taking dx away from this in the positive direction, and this is shear is V at x plus dx. Alright. If V is varying from x to dx, this will show up as a different value compared to this by a small difference in the value. Okay. And if I can connect these M of x plus dx, V of x plus dx to Vx and see what we get, this may probably give a sense of the relationship between shear force and bending moment. Let us do that exercise. What all equations can we write from this? Definitely one equation that I can write is vertical equilibrium. Sigma f along y, let us say upward like this, is positive, equals 0 if it is in static equilibrium, the other is bending moment about a particular point. I can choose a center or one of the edges and draw the and find out the equilibrium of that. So, let us say M at a particular point, let us say in this particular case shall we choose this center, M at O equals 0. We have already learned that we can take any one of those points in order to write down these moments. Let us see what we get out of these. Let us first start with sigma Fy equals 0. What all will take part in it? This shear force Vx, this shear force Vf x plus dx and W. Okay. So, let us write one by one. This is negative in direction, so minus Vx, this is positive, so plus V of x plus dx, okay, and there is a load over here distributed over this length which is dx. So, W times dx is the total force and it is acting downward. So, minus W times dx, the total should be equal to 0 for static equilibrium. So, this immediately reveals, I am going to write this in a way that you already know. Is equal to W times dx. I am going to take dx down like this. Okay. Am I correct in the sign? Yes, I have taken W over to the other side. This is, remember, this is W at x. Okay. What is this? Limit. Let me just correct myself and write it as delta x here, small length. So, I am going to have delta x here, delta x here. Limit as delta x tends to 0, what is this? It is nothing but dV by dx, and that is equal to W of x. And therefore, we have a relationship. It essentially tells me that the variation of shear force along x gives me W of x, which is the load applied, transverse load applied. Okay. So, one result that we get is dV by dx equals W of x. We will get one more result from this. Let us do that separately. Okay. To be specific, I will write it as W of x. Let me denote all the forces. This is V at x, this is M at x, M at x plus dx. Notice that I am using positive sensor all of them, and this is V at x plus dx. Okay, I have represented all the forces, and this length, let me again make this as delta x so that we are clear about it. Now we seek to find the moment equilibrium at a particular point. Which point is better to choose here? We will choose one of those points. Shall we choose a point here, or a point here, or a point here? If I choose a point over here, I will not have this shear force coming into picture. If I choose a point over here, remember this particular load is equally distributed, and therefore that will not contribute to the moment over here. Okay. If I take this, V of x will not contribute to it. Okay. Either way, it does not matter. Let us choose at the center. Okay. So, O. Okay. Please remember this is at a distance delta x by 2, delta x by 2 away, right. This is equal to 0 will imply, let us take one after the other. This m of x is in the clockwise sense, so minus m at x. As a shear force that is acting downward like this will produce a counterclockwise moment, and therefore it is plus v at x times delta x by 2, right. We have accounted for this, and this force will have a resultant over here and another resultant over here, those two will cancel each other. So, I am not going to bother about moment due to W of x. To the right hand side about O, m of x plus delta x is in the anticlockwise sense. So, it is positive m at x plus delta x, and the other bending moment contribution is from v of x, and that is also counterclockwise, and that is v of x plus delta x times delta x by 2. Okay. Have I left out anything? Nothing else. This is equal to 0. Okay. Notice that we have m of x plus delta x minus m of x. So, let us write it down, m of x plus delta x minus m of x, okay, plus v of x plus delta x, v of x plus v of x plus delta x, both multiplied by delta x by 2 is equal to 0, right. Dividing throughout by delta x, we will have m of x plus delta x minus m of x by delta x by 2. I am going to divide by delta x by 2 is equal to, I am going to take the other to the other right hand side, minus v of x minus v of x plus delta x. Okay. Now, if I take the limit as delta x tends to 0, I know m of x plus delta x minus m of x by delta x tending to 0 will give me dm by dx, and I have a by 2 which upon going up will give me 2 times dm by dx is equal to minus of, when delta x tends to 0, this will be v of x, this is already v of x. So, we will get minus 2 v of x, is that all right. So, cancelling these 2's here, we get dm by dx equals minus v. Okay. And therefore, in this relationship we got one more, which is dm by dx is equal to minus v. So, we have two relationships that we could find out from equilibrium of a small infinitesimal element for a beam which has transverse force acting on it. Remember, in this particular case I do not have to bother about what support reactions and all those, that will come into play in an automatic sense. One more thing to note here is I have dv by dx is equal to w of x, but v is equal to minus dm by dx, and therefore I can now write d of minus dm by dx is equal to w of x, right. What is this? this is nothing but minus d squared m by dx squared is equal to w of x. So, I am going to take this minus over to the other side, which is minus w. Okay. So, if I know how the force W is varying, I can find out how shear force is going to vary. If this were a constant force, what do you conclude for as far as variation of V is concerned? dV by dx is constant, which means V is linear. If V is linear, dm by dx is one order, m has to be one order higher than V, so that m has to be quadratic. Okay. So, for a constant W, I have a linearly varying V. For a linearly varying V, I have a constant m. So, these are the results that we got. Let us observe and find out what all we understand from this. When there is no, for example, if I have a beam like this, let us say we will take that particular example where we had a P acting, 2P acting at L by 3, L by 3. Okay. What do you see in this zone? In this zone, W of x is equal to 0. There is no force acting in between. Okay. And therefore, what should I notice as far as dV by dx is concerned? dV by dx is equal to 0 implies V is a constant. So, in this particular region, when we drew shear force diagram, we found that the shear was not varying between this point and this point. Okay. All right. If shear force were constant and I use this fact over here, we have a dm by dx is equal to constant, because in this region V is a constant, which means this is a constant, negative constant, means m is now linearly varying. This implies that m is linear. On the other hand, the example that we took for uniformly distributed load, for this case, if you remember, we had shear force diagram something like this, WL by 2, and it was 0 at this point and it was varying linearly like this. Is this correct? From this conclusion, W is a constant, which means dV by dx is a constant, means V is linear. So, I get a linear variation. Similarly, if I have to draw the, and this is shear force diagram, if I draw the bending moment diagram, dm by dx is equal to minus v of x. I can use this fact to draw it or from the basic free body diagram I can draw, and I got it to be something like this. The positive value and the center was equal to WL squared by 8, if I remember correct, and it was the maximum at the center. Is that correct? Let us look at this particular point. This particular point, V is equal to 0. If V were equal to 0, dm by dx is equal to 0. When do you have dm by dx equal to 0? If there is a function m of x and I want to find out the maximum or the extremum value of m of x, I take the derivative and set it equal to 0, and that is basically what I can do here, and I will get dm by dx to be 0, or in other words m is maximum, and therefore I have maximum value over here. Okay. Or in other words, the slope of this distribution at this point is horizontal equal to 0. Okay. So, there are some conclusions that you can make. For example, in a beam where I want to find out where the maximum bending moment would occur, it is enough to draw the shear force diagram, find out where zeros are existing in shear force, and that will immediately tell me where I should be finding out the bending moments. Okay. So, that is the advantage of using these expressions. Thank you.